Welcome back to another explainer. Today, we're taking a really hard look at a problem that's basically plaguing almost every developer working with generative AI right now. We're talking about moving Retrieval-Augmented Generation, or RAG apps, from those super fragile, perfect world prototypes into reliable, actual battle-tested production systems. Because let's be real, if you've ever built a RAG app that worked absolutely flawlessly on your laptop, only to watch it completely unravel in the real world, well, this explainer is exactly what you need. To really set the stage here, let's look at this observation from AI product architect Chidozie Manigwu. He hit the nail on the head when he said, most LLM applications look great in a high-fidelity demo. Then they hit the hands of real users and start failing. And honestly, that completely validates the exact pain point of deploying RAG. It's incredibly easy to build a demo that impresses your team, right? But it is incredibly difficult to build a system that doesn't just randomly hallucinate or crash the second actual users start throwing unpredictable questions at it. Okay, so let's dive into our roadmap for today. We'll start with the RAG reality check, move on to the lost context problem, and then explore the late chunking solution. After that, we'll cover essential production guardrails, and finally wrap up with testing using AI evals. Section 1. The RAG reality check, diagnosing the demo illusion. So, this source material points out that these naive systems fail in some very, very predictable ways. First off, they start answering questions they really shouldn't be answering. Second, they break the second document retrieval gets weak. Third, they just time out due to network latency, which creates a massive user-facing outage. And honestly, the absolute worst part, they fail silently. Because there are no structured logs or tests, literally nobody can tell if a bad answer was caused by weak retrieval, a confusing prompt, or just some random model update. You're essentially flying completely blind out there. Moving on to Section 2, the lost context problem, why standard chunking fails. Think about a standard RAG pipeline, the classic chunk then embed strategy. If a user asks a simple, relatable query like, what is the population of Berlin, you might think your system can handle that in its sleep. But let's actually look under the hood at how naive chunking processes the underlying text. With naive chunking, an article is basically just chopped up blindly. Chunk 1 might isolate the word Berlin, while Chunk 2 ends up trapping the actual population figure. Standard chunking literally shatters the relationship between the city and the number. By encoding them totally independently, your correct chunks might not even get retrieved. In an ideal world, the city and its population absolutely must remain mathematically connected. Let's look at a slightly more technical example from the Afterthoughts repository. Imagine you're parsing a technical report. The first chunk says, the new lithium-sulfur battery achieved 400 watt-hours per kilogram. Okay, great. But a later chunk says, its cycle life remains a challenge. If you embed those sentences separately, that second chunk totally loses its connection to the lithium-sulfur battery. Pronouns like it become completely meaningless to the system. So your search for lithium battery limitations will completely miss the answer, leaving your LLM basically grasping at straws. Section 3. The late chunking solution, inverting the pipeline. So instead of splitting the text naively, late chunking totally inverts the process. It's a real game changer. Step 1, embed first. You pass the entire document, or as much of it as possible, through the transformer layers of your embedding model. That gives you token embeddings that actually reflect the global context. Then, step 2, chunk second. You apply mean pooling to the token embeddings to form chunks, but only after the model has established that cross-chunk context. This brilliant little flip ensures that pronouns, references, and all those vital contextual cues are perfectly preserved in a single forward pass. To actually implement this in your stock today, our sources highlight two really powerful tools. First up is Chonkie. It's a super lean chunking library that makes adding late chunking to retrieval pipelines like KDB AI or other vector stores extremely simple. And second, we have Afterthoughts, which gives you deep sentence-aware transformer flexibility and integrates beautifully with HuggingFace. Now, if we drill down into Afterthoughts for a second, it offers some serious production-grade optimizations. It allows for highly flexible configurations, letting you test token or sentence-based chunks side by side. It also gives you structured output via polars or pandas. But critically, for production environments, it uses automatic mixed precision, or AMP, to increase inference speed. It also allows for dimension truncation, which significantly reduces your memory footprint without requiring you to go back and retrain your models from scratch. All right, Section 4, Essential Production Guardrails, Fortifying the Backend. To understand why we even need these guardrails, we first have to define a massive core problem: forced hallucination. If your app retrieves irrelevant chunks of text and you just blindly pass them to the LLM, the model is going to try to bridge the gap and invent an answer anyway. Without a designated I don't know pathway built into your system, you are essentially forcing the LLM to hallucinate. You're forcing it to lie to your user. To build up our defense against this, we really lean on our vector store. Our source specifically highlights FAISS, that's Facebook AI Similarity Search, developed by Meta AI Research. FAISS is this lightning-fast library that stores our embedding vectors and compares them using L2 distances and inner products. It's what quickly answers the million-dollar question, which document chunks are mathematically closest to what the user just asked? Notice this specific threshold, 0.30. When you're using normalized cosine similarity in phase, this is the highly recommended baseline. It's your starting point for building a really defensive architecture. We actually use that exact threshold to build what's called a retrieval gate. Think of this gate as a bouncer for your LLM. Here's how it works. Step 1, you retrieve the top K chunks from FAISS. Step 2, you evaluate that top similarity score. Step 3, if that score is below our 0.30 threshold, well, the context just isn't good enough. The system stops right there and safely refuses the query. Step 4, you only call the LLM if the gate passes. This single, elegant mechanism aggressively cuts down on those forced hallucinations we talked about earlier. But look, a gate isn't quite enough on its own. You also absolutely need the backend stability trifecta. First, you must force the LLM to return structured JSON outputs. If your backend is sitting there expecting a clean list of sources, but the LLM returns a bunch of chatty conversational filler, your code is going to crash. JSON prevents that. Second, you have to implement fallback behaviors for API timeouts so the user gets a helpful message, not just a broken screen. And third, keep your prompts centralized so they are actually easily versionable. Finally, Section 5, Testing with AI Evals, Preventing Regressions. The harsh reality here is that RAG outputs are probabilistic. Because AI is just fundamentally unpredictable, traditional software unit tests that rely on static string matching, they simply will not work anymore. We need a proper evaluation harness that continuously tests a set of golden questions against our system. So what do these evals actually test? Well, they run end-to-end against your API endpoint to actively check for expected behaviors. For example, does the app correctly refuse a query when the retrieval is weak? When it does provide an answer, does it strictly include the correct sources? And probably most importantly, is the system's behavior stable across prompt tweaks and underlying model changes? This is exactly how you catch those silent regressions before your users do. Wow, we've covered a lot of ground today, from late chunking with Afterthoughts and Chonkie to FAISS vector search and, of course, building robust retrieval gates. But I want to leave you with this final, somewhat provocative thought to reflect on. If your RAG system isn't allowed to say, I don't know, can you ever really trust what it actually does know? Building a reliable application means designing it from the ground up to be measurable, predictable, and safe. Thanks so much for joining me on this explainer, and I'll catch you in the next one.